Just to summarize, this experiment is carried out to determine the coefficient of performance (COP) for vapor compression cooling system and to investigate the effect of flow rate condenser on the compressor power. For introduction and theory part, it discusses about the flow and working operations of vapor compression refrigeration cycle in details. Based on the methodology section in the report, it tells about the steps involved while conducting the experiment. While the results section shows the recorded value of rate of heat transfer at evaporator and condenser and the COP values for different flow rate of water to condenser. Instead of that, the discussion section shows the graph plotted using the result obtained and discussed in more detail based on chemical reaction engineering theory. It explained the effects of changing the condenser flow rate of T1 till T6 to compressor power. The error and recommendation to avoid mistakes while doing the experiment are also shared in the discussion. The conclusion section concludes all the objectives and calculations of this experiment.
I will explain about the introduction and theory part. Okay, so first thing first, we have to know that the objective of the experiment is to determine the coefficient of performance COP for vapor compression cooling system. Vapor compression refrigeration, in which the refrigerant undergoes phase shift, is the most extensively used method for air conditioning buildings and automobiles. It's also used in refrigerators, large-scale warehouses for chill or frozen food and storage, refrigerated truck and railroad cars, and a variety of other commercial and industrial services. Okay, so among the various types of industrial that use big vapor compression refrigeration systems are oil refineries, petrochemical and chemical processing plants, and natural gas processing plants. Okay, next, vapor compression uses a circulating liquid refrigerant as the medium which absorbs and removes heat from the space to be cooled and subsequently rejects the heat elsewhere. Such systems have four components, which is a compressor, a condenser, a metering device, a thermal expansion valve, and an evaporator. And then circulating refrigerant enters the compressor in the thermodynamic state, known as saturated vapor, and is compressed to a higher pressure, resulting in a higher temperature as well. The hot compressed vapor is then in the thermodynamic state, known as superheated vapor, and it is at a temperature and pressure at which it can be condensed, with either cooling water or cooling air flowing across the coil or tubes. Because of its ability to cover a wide variety of heating and cooling intended temperatures by varying pressure, vapor compression refrigeration systems play an important role in the chemistry process industry. Okay, so for the theory part, according to the second law of thermodynamics, heat cannot be transferred from low temperature to high temperature unless additional work is involved. Devices used for the transfer of heat are called refrigerators, and the working fluid is called refrigerant. Cooling system receives heat from the low temperature space and transfers heat to the high temperature space. This process required work, which is W, to be supplied to the system as depicted in the figure. So we can see that the figure was a schematic diagram of a refrigeration system. So Q1 equals to magnitude of heat rejected to the warm space, and Q2 is equal to the magnitude of heat removed from the refrigerated space. Okay, and then the refrigerant reaches the compressor as a vapor and is compressed to the condenser pressure as shown in figure 2. It exits the compressor at high temperature, cools and condenses as it passes through the condenser coils, releasing heat into the environment. Then it reaches a capillary channel where the throttling effect causes the pressure and temperature to drop. The low temperature refrigerant is pumped into the evaporator where it absorbs heat from the refrigerated room and evaporates. The cycle is completed after the refrigerant leaves the evaporator and re-enter the compressor. So the coefficient of performance, which is COP, can be calculated based on the following equation, which is COP equals to cooling effect divided by work net in.
For the methodology part, the apparatus used is Refrigeration Cycle Demonstration Unit R633 PA Hilton using R14 refrigerator fluid. For the procedure part, according to the video uploaded, the first step is the valve was opened and the pipe was turned on and the water flowed to the evaporator and condenser at the rate of 26 grams per second. The second step is the device was switched on. The cooling system was allowed to be stable at approximately 10 minutes. The third step is the reading of temperature 1, temperature 2, temperature 3, temperature 4 were recorded by adjusting the temperature selector switch and the reading was taken at the temperature indicator. The fourth step is the reading of the pressure gauge of condenser and evaporator was taken. The fifth step is the reading of temperature 5, temperature 6 and temperature 7 were recorded manually. The sixth step is the temperature was repeated by changing the flow rate of water condenser between 26 to 4 grams per second. The seventh step is first set of experiment was carried out. Eighth step is after the experiment was done, the flow rate of condenser and evaporator was turned to 0. And the ninth step is the main switch was switched off. The water supply was turned off after 1 minute is the 10th step. And the last one is the valve was closed to the shutdown position after that 1 minute. That's all. Thank you.
So let's start with the results part. So the table given, and the table shows the readings of absolute condenser and evaporator, gauge pressure of condenser and evaporator, power input of compressor and the temperature of water for inlet and outlet of evaporator, and condenser for every 10 minutes for 5 times. The water temperature before entering evaporator was T1 while water temperature after entering evaporator was T2. The water temperature after entering condenser was T3 and water temperature before entering the condenser was T4. The temperature of the evaporator was indicated as T5 whereas for condenser it was T6. The final temperature T7 was the temperature for the compressor. Rate of heat transfer at evaporator and condenser and also the coefficient of performance COP of the refrigerator were also calculated and tabulated in the table given. Moving on to the next part, which is the discussion part. So the first discussion will be calculate the rate of heat transfer that occurs in the evaporator and the condenser for the 5 test runs and discuss the results. So to find the rate of heat transfer, the formula can be used is Q equals to M, which is the mass flow rate, and times with the Cp, which is the heat capacity. In this case, we will use the heat capacity of water and also the change in the temperature. So for the M, which is the mass flow rate given is 19 gram per second. So we have to change the unit to kilogram per second. We will get 0.019 and the mass flow rate is the same for all the 5 test runs. So when calculated, the rate of heat transfer for the first test run will be 0.135240 kilowatt, and for the second test run will be 0.0715977 kilowatt. The third test run will be 0.0397765 kilowatt. The fourth one will be 0.0238659 kilowatt, and the last one for the fifth test run is 0 kilowatt. So to find the rate of heat transfer in condenser, which is QH, the same formula is used, just that the mass flow rate is given for the all the 5 test runs are different. So the first mass flow rate is 0.018 kg per second, the second mass flow rate is 0.016 kg per second, the third mass flow rate is 0.012 kg per second, the fourth one is 0.08 kg per second, the fifth one is 0.04 kg per second. So the answer for the rate of heat transfer in the first test is 0.1205856 kilowatt. The second rate of heat transfer for the second test run will be 0.133984 kilowatt. For the third test run, the rate of heat transfer is 0.12561 kilowatt. The fourth test run will be 0.07704008 kilowatt, and the last one for the fifth test run, the rate of heat transfer in condenser is 0.066992 kilowatt. So after getting all this value, we can calculate the coefficient of performance for the refrigerator with the formula of absolute value of QL, which is the rate of heat transfer in the evaporator, divided by the work net. The work net is equals to the difference between the rate of heat transfer in condenser and also the rate of heat transfer in the evaporator. So the coefficient of performance for the first test run is 9.22857114. The second one will be 11476510. The third one will be 0.4634146. The fourth one will be 0.44888189, and the last one will be 0. The second discussion part will be explain the effects of changing the condenser flow rate of T1 to T6 to compressor power, and draw the graph and discuss the results obtained. So the first graph of temperature versus condenser flow rate is plotted, and from the graph we can see that the temperature affects the flow rate in the condenser, where the condenser flow rate increases. From the graph we can see that for all the temperatures T1 to T7, when the temperature decreases, the condenser flow rate increases, except for temperature 2 and also temperature 5. This is because maybe there are some errors occurred during this experiment, but from the data given we can see that when the temperature decreases, the condenser flow rate increases. The next graph is plotted where it is compressor power versus the condenser flow rate. So based on the graph we can see that the compressor power increases during test 1 to test 4 and drop drastically from test 4 to until test 5, which is from 274 watt to 221 watt. So it shows that when the condenser flow rate increases, the compressor power also increases, but at one point it will drop drastically. During the experiment conducted, there might be some errors occurred. So one of the errors in the experiment is the temperature and the power reading, which is constantly changes as we record the readings from electronic thermometer and wattmeter. So this error can be reduced by taking a few readings and take the average readings of temperature and also power. The next one will be the parallax error, where when taking the temperature reading from thermometer, we might have occurred. So in minimizing this error, the position of the reader's eye must be perpendicular to the scale of the thermometer. That's all from me. Thank you.
To sum up, based on this experiment, the rate of heat transfer at evaporator and condenser were calculated at 5 different condenser flow rates of T1 till T6 to compressor power of the vapor compression refrigeration cycle. With the state point properties and the power drawn by the compressor, the COP can be determined. However, the COP can be determined from the work input to the compressor or as the work applied to the working fluid. The rate of heat transfer at evaporator and condenser at T1 till T6 are: for evaporator at T1 0.1352401, at T2 0.0715977, at T3 0.0397765, at T4 0.0238659, and at T5 0. And for condenser, T1 0.120586, T2 0.1339840, for T3 0.1256100, for T4 0.0770408, for T5 0.06699. And for the coefficient of performance, for T1 is 9.22857114, for T2 1.14765110, for T3 0.463446, for T4 0.44888189, and for T5 is 0. By comparing with the ideal vapor compression refrigeration cycle, data obtained and calculated from the laboratory, which is actual results, differed from those of the ideal cycle. This is because due to the assumption of that the compressor is isentropic, Thus, it shows the greatest impact on the variation of the ideal and the actual cycle. The assumption was made to simplify the calculations when it deals with the ideal cycle of vapor compression refrigeration. This occurs due to some errors during the experiment, such as the accuracy of the measuring equipment and the methods used in obtaining the measured values. Moreover, the actual cycle would greatly approximate that of the ideal cycle if the assumption could be reached, such as constant pressure heat transfer across heat exchangers and the reduction of heat transfer to and from the environment due to insinuated devices. Thank you.